Elliptic curve-based Diffie-Hellman key exchanges have the same sequence of actions taking place as the classic Diffie-Hellman key exchanges, but work against elliptic curves as the underlying mathematical entities. For this, the participants, like Alice and Bob, agree on an elliptic curve to be used, and then each first sampling a private key individually and in isolation. With these private keys then created, Alice and Bob create half keys by multiplying their private keys with the point G that serves as a generator on the chosen elliptic curve. Once the resulting half keys are exchanged, both Alice and Bob can calculate the shared key by multiplying the half key that they received with their own private key. Various elliptic curves exist, and in the following I will demonstrate the implementation of an elliptic curve-based key exchange based on the curve P-256, which is one of the most widespread curves implemented. P-256 was defined by NIST in Special Publication 800-186, where the curve definition can be found in Chapter 4.2.1.3 on page 13. P-256 is then just a normal Weierstrass elliptic curve, meaning that during the implementation of the P-256 based elliptic curve key exchange, I was able to fall back onto standard algorithms for the addition and multiplication of points on elliptic curves. Implementing P-256 for an elliptic curve key exchange sounds very exciting, so let's get started with the demo. To implement a P-256 based elliptic curve Diffie-Hellman key exchange, I first had to get the P-256 curve into my code. The definition of this curve can be found in the NIST Special Publication 800-186 in Chapter 4.2.1.3, and for the curve parameters I had to fetch the prime modulus P with the order n, the Weierstrass coefficients A and B, as well as the x and y coordinates of the generator point used during the key exchange. Once I copied these values over, I then decided to write two minimalistic classes in order to create elliptic curves with points on these curves, and to later define a multiplication for these elliptic curve points, where the P-256 curve is defined by the modulus P, and the Weierstrass equation coefficients A and B, and the generator G is a point on the P-256 curve with the x and y coordinates as given. Once these minimalistic classes were created, I proceeded to outline the steps required to go through the execution of the key exchange, which was to create a public-private key for both Alice and Bob, then for Alice and Bob to each calculate the shared key based on the half keys that they received from the peer, and to finally assert that the shared key of both Alice and Bob are the same. The private key of Alice really is just a randomly sampled value from 1 to the order n, which I delegated to a function to implement later, and the public key of Alice is just the P-256 generated G multiplied with the private key of Alice. This is a scalar multiplication for elliptic curve points, which I will later have to implement for the elliptic curve point class, and which means that Alice's public key is a seemingly random point on the P256 curve. The public-private key creation for Bob is the same like for Alice, and with both key pairs generated, Alice could then derive the shared key by making use of her private key and the public key of Bob by again just multiplying her private key with the public key of Bob, which is again a scalar multiplication on elliptic curve points. The shared key calculation for Bob is similar, and to verify that Alice and Bob arrived at the same shared key, I wrote the final assertion statement that ultimately needs to be passed when executing this key exchange. First function I then proceeded to implement was the generation of random private keys on P256. The recommendation on how to do this can be found in NIST FIPS publication 186.4 in chapter B.4.2, which outlines that this is just a random sampling of a value from 1 to n-1. With this done, next one up was the implementation of the elliptic curve scalar multiplication. For this, I fell back onto the well-written Wikipedia site for elliptic curve point multiplication, which, in chapter 3.1, presents the quite concise double and add approach, which I then tried to replicate very closely within Python. To implement this, it was clear that the curve needs to have an infinity point and that an elliptic curve point addition function needs to be available. Creating infinity on a curve I did by creating a point on the curve with x and y coordinates as none. The addition is also well described on the Wikipedia site in chapter 2, stating that 3 special cases lead for the addition to result in infinity. First 2 cases are if either of the points involved is infinity, or if the 2 points involved are the inverses of each other. Then formulas are defined for the case if the points involved are distinct and for the case that the points coincide. Once these were implemented, I went back to the driver of the elliptic curve exchange to verify that the P-256 based elliptic curve key exchange really led for both Alice and Bob to arrive at the same shared key. This was successful, and I thought it's quite cool to see how an elliptic curve based key exchange works in Python.